Let's take a look at a topic called L'Hopital's rule. And this is a relatively sort of quick principle that we can use that sometimes is going to help us to evaluate limits. We've already seen how we can use Maclaurin series and series expansions to evaluate limits. But depending on how the exam question is structured, like if it's leading you down the route with differentiating and you've got your second derivative, you've got your third derivative, you're obviously going to be doing a Maclaurin series expansion. But if it's just like a quick limit question, like evaluate this limit, you could still do it using a series expansion, but there's another technique that we can look at, which is called the L'Hopital's rule. And essentially what that tells us is if our original limit is like 0 divided by 0, or infinity divided by infinity, instead of thinking about this original limit of like the function on top divided by the function on the bottom, we can instead think about, well, that limit there would be the same as the limit of the derivative of the function on top divided by the derivative of the function on the bottom. We're not doing like a quotient rule or anything, we're not differentiating the whole thing, we're just looking at whatever's on top, we're differentiating it, we're looking at whatever's on the bottom, and we're differentiating it. So this original limit that we couldn't figure out, we might be able to think about the derivative instead, and that limit will be the same as that limit. So it's like a nice quick way of evaluating limits. Let's start with an example. So we're thinking about as x tends to 0. Now clearly as x tends towards 0, sine x tends to 0, and x also tends to 0. So what we've got here is we've got 0 divided by 0. So at the moment we can't determine what this limit's going to be. But because it is 0 divided by 0, we could apply L'Hopital's rule. So I would say, well, that would be equivalent to the limit as x tends to 0. Differentiate the top, we get cos x. Differentiate the bottom, we get 1. So we don't get this problem anymore, like we haven't got 0 divided by 0 anymore. And we could say that, well, as x tends to 0, cos x tends to 1. So this limit would just equal 1 divided by 1, which would be 1. Okay, let's try another one. So the next one we're thinking about as x tends towards e, and we've got ln x minus 1 divided by x minus e. So clearly you can see, well, as x tends towards e, we've got 1 minus 1 divided by e minus e. Essentially we've got 0 divided by 0, haven't we? Because ln of e, don't forget, is 1. Sometimes people get a bit freaked out by that. ln of e to the power 1 is just 1, isn't it? So this original limit that we're being asked about is 0 divided by 0. So instead we could say, well, that's the same as the limit as x tends towards e. The derivative, so if you differentiate ln x, you get 1 over x. Differentiate 1, it becomes 0. Differentiate the bottom, x becomes 1. E, don't forget, it's just a constant, like 2.718. This is just a number. So when we differentiate that, it becomes 0. And now we can see that as x tends towards e, we've got 1 over x. So this would be 1 over e. Or e to the minus 1. So just think about it, like initially we had something which was 0 divided by 0 is completely undefined, or we're not able to evaluate that, are we? But by using this process, L'Hopital's rule, we can actually see that this does tend towards the limit, which is a value that we can evaluate. Okay, let's try another one. Okay, so for example 3, we've got the limit as x tends to 0 of 1 minus cos x divided by x squared. As x tends to 0, this would be, don't write equals because it's not, but that would be 1 minus 1 divided by 0. In other words, we've got 0 divided by 0. Okay, so we can't evaluate this as it stands. We can then instead apply the L'Hopital's rule and say that would be the limit as x tends to 0 of minus cos differentiates to sine. X squared differentiates to 2x. And then you might think, oh, well, this doesn't work because, like, think about it, as x tends to 0, we've still got sine x, which is 0, so we've still got 0 divided by 0. But the beauty of this technique is that you can apply it more than once. Like, this limit here is the same as this limit, which is still 0 divided by 0. But because that limit's the same as that limit, we know that, well, that would be equivalent to the derivative divided by the derivative. So we can keep going. Like, we can say, well, that would be the same as the limit of the derivative of this divided by the derivative of this. Like this, these derivatives, if that limit is the same as that, then the derivative would be the same as the limit before as well. Okay, so that would give us cos x divided by 2. So this now can be evaluated. Okay, just maybe highlight that in your notes, because I do think if this comes up, you'll probably be applying it maybe 2 or 3 times. So now we can evaluate this and say, well, as x tends to 0, cos of x tends to 1. So this limit, as x tends to 0, what the original limit that we were being asked about, would be equal to a half. Okay. This technique could potentially allow us to think about, there's like a special type of limit that we need to know for the A level. So we're going to do one more example, which is going to provide us with like a really useful limit that we're going to see mainly on the next topic that we move on to, which is all about integration. Okay, but we can apply this rule to see where it comes from. So what we're going to be looking at is, this is like there's 2 special limits. The first special limit that we can see in this video is the limit as x tends to 0 of x to the k ln x. I think let's do an example first before we do like the general one. If I was thinking about the limit as x tends to 0 of x squared ln x, you can't just evaluate this, like, because if you break it down and think about it, right, as x tends to 0, x squared tends to 0, but ln x does something weird, doesn't it? Like, as x tends to 0, if you think about the log graph, as x tends towards 0, the log graph tends towards minus infinity. So what we've got here really is we've got something that's tending towards 0, that one's trying to get smaller, and that one's trying to tend towards minus infinity. So like, essentially we've got like 0 times by minus infinity. And you'd be like, well, that's a bit weird, what's going to happen there? We don't know, like, which one's going to win? Okay, does the polynomial win, or does the log win? And a good way of thinking about it is the logs are quite lazy, like the logs do things really slowly, so the polynomial ends up winning. Like that one there, if you see the answer's 0, isn't it? So even though that one's going towards minus infinity, the polynomial goes towards 0 quicker, and this one wins the fight. If there's one with exponentials as well, exponentials win. Like, exponentials do things really quickly. So if there's an exponential in there, that one's going to win. If there's a polynomial, that's like the next quickest. And then the logs, like, think about it as like lazy logs. Logs do things slowly. But we want to actually think about how we can prove this result. Okay, and the answer is going to be 0. It's not an indeterminate form, like it's not 0 divided by 0 or infinity divided by infinity. So first of all, we're going to have to write it. Instead, as we could write it as the limit as x tends to 0 of ln x divided by x to the minus 2. Because now we've got a fraction, and think about it, if it's x squared on the bottom, you could bring it down and write it as x to the minus 2. because that's just, if you brought that up, the minus minus would be back as a positive, wouldn't it? But now the beauty of this is we've got a fraction, and we've got infinity divided, like if you think about it as x tends to 0, ln x tends towards minus infinity. 1 over x squared tends towards infinity. Like as x gets smaller, this would tend towards infinity. So we've got like a form that would allow us to use the Hopital's rule. Okay, so let's differentiate and see what happens. So that would be the same as the limit as x tends to 0. ln x would be 1 over x times by the power, take 1 off the power. Okay, so we've got minus 2x to minus 3, which we could write as if you got x to the minus 3 on the denominator, when we bring it up, it would become x cubed, wouldn't it? Okay. And we're dividing by the minus 2, so that's still going to be minus a half. Bit awkward with the index form, this, like people can get into a bit of a mess with this, but like if you think about it, if you're dividing by this, if I bring it up, that's going to become x cubed, but don't bring it up and make it a times by 2, like that we're still dividing by 2. If you want to bring that up, you could write it as 2 to the minus 1, but it's still going to be a half, isn't it? Okay, so we've got minus a half x squared. So now we can see, well, as x tends to 0, this clearly is going to tend towards 0, isn't it? Okay, so let's apply like the same logic for the general form x to the k ln of x. So we could say that's the same as the limit as x tends to 0 of ln x divided by x to the minus k. And then we can differentiate using the Hopital's rule. Times by the power, take 1 off the power, so we can rearrange this. And we'd end up with x to the k, because we're dividing by this, so then we've got a polynomial that we can evaluate now, can't we? Because we've got x to the 1 on the bottom. And then if you're doing x to the k plus 1 divided by x to the 1, you just get x to the k. You got to be confident with the index form here. You're bringing this up, aren't you? So when we bring this up, the power becomes negative, so minus minus becomes positive. Okay, and then we can clearly see that because k is greater than 0, x to the k, like x squared, x cubed, you know, as x tends to 0, x squared or x cubed or so on, would also tend to 0. Okay. So not, I mean, this bit's a bit abstract, isn't it? But it's not actually that bad. You'll try a couple of questions. Essentially, if you just get a limit that you're asked to evaluate, and like just think about exam technique, right? If it just hits you with a limit and doesn't mention like any sort of derivatives or series expansions, just quickly check, how could I use the Hopital's rule? Like, can I just differentiate the top and the bottom? Because if it's something that you can easily just differentiate on the top and the bottom, the limit might fall out like really quickly. Okay, nice one.